Hello students, today's our topic of discussion is anomalous Zeeman effect. As we know that in vector atomic model we consider two motion of electron, one is spin motion and another is orbital motion. Due to spin motion there comes into existence two type of angular momentas. One is spin angular momenta, that is mechanical momentum, that will discuss the mechanical motion of the electron in the spin motion, and another is the spin magnetic momentum, that is the magnetic field produced by the motion of the electron when it is giving its spin motion. Second, when the electron is moving in its orbital motion, again we have two type of momentas. One is our angular or mechanical momenta and another is the magnetic field produced by this electron, that is a charged particle in a closed loop. And very well know that this is known as our orbital mechanical angular momentum, and this is our orbital, that is magnetic momentum. It means due to these two motion, one is a spin motion and another is orbital motion, we get total four types of motions. Two are angular motions and two momentums or two motions are representing the magnetic field produced by the two type of motion of the electron. And in the last discussion in normal Zeeman effect, we found that the ratio of magnetic momentum, orbital magnetic momentum to the orbital angular momentum is E upon 2 m naught, where E is defined the charge on an electron and m naught is the rest mass of an electron. And in quantum mechanics, the angular momentum, orbital angular momentum, it is given by L star h cross, where L is depending upon the orbital angular quantum number, that is orbital quantum number L, and this is our Planck's constant divided by 2 pi, that is a constant quantity. Similarly, in case of spin motion, the magnetic momentum in spin and the spin angular momentum is given by E divided by m naught, where again is the charge on an electron, m naught is the mass of an electron. And if we substitute the value of angular momenta in terms of our spin quantum number, which is in quantum mechanics given as s into s plus 1 under root, we will find out that we will have a relation in between the orbital magnetic momentum and orbital angular momentum given by Eh upon 4 pi m naught with L star, and similarly we will have mu s, that is the spin magnetic momentum in terms of our spin angular momentum, that is Eh upon 4 pi m naught, but here we have two times as compared to the orbital motion, and again we have s star, which will give us the value of our spin angular momentum. If we draw these momentas in terms of vector, we will find out that these angular momentas and these magnetic momentas combine together to give a resultant magnetic momentum of our atom. Let us consider this is our atom, and in our atom we have total spin quantum number is s, and corresponding to spin quantum number s we have an spin angular momentum, and now we are denoting it with s star. Similarly, with respect to the orbital motion, let us consider the total orbital angular momentum of our given atom is indicated by L star. And as these two are two vector quantities, and if we apply here the parallelogram law of vector addition, we very well know that we will have the diagonal as a resultant, and here we are giving J star as our resultant vector, and this is known as our total angular momentum. Corresponding to this motion, there is a magnetic field, and the magnetic field direction is opposite to the spin angular momentum because the electron have negative charge. It means the direction of mu s and s star is always opposite to each other, as electron have negative charge. Electron have negative charge, so we have the anti-parallel direction of s star and mu s. Similarly, due to this negative charge again, due to the orbital motion of the electron, we have an orbital magnetic momentum, and here the orbital angular magnetic momentum is represented by mu L, and these two quantities are not equal, so we are not getting the resultant in the opposite direction of J star. We will have a resultant somehow deviated from the opposite direction of J star, and let us consider thus this resultant is indicated in our case with the help of mu ls, that is mu ls is representing the total magnetic momentum of our given atom, where J star is representing the total angular momentum of our atom. According to our assumption, J star and mu ls should be in opposite direction, but as mu L is not equal to mu s, so the mu ls is not in the direction of, we can say that it is not in the direction of mu j, and the direction of mu j is opposite of the direction of our total angular momentum j. Now we will find out our net resultant magnetic momentum in this case, and the net result magnetic momentum, that is the magnetic momentum opposite to our total angular momentum, that is J, is here we are representing it with mu J, and we can easily find out the value of mu J with the help of the value of mu L and mu S. If we get the horizontal component of mu L along mu J, and similarly the horizontal component of mu S along mu J, then we will get the resultant value of our total magnetic momentum. If these are the horizontal component of mu L and mu S, it means this is the vertical component of mu L, and as mu L is moving around or rotating around the total angular momentum, it means this vertical component of mu L have different values in an atom. Similarly, if we are taking the horizontal component in the direction of mu j of mu s, then we will get the vertical component perpendicular to our horizontal component, and as this magnetic momentum is moving around our resultant magnetic momentum, and due to this rotational effect of our mu s around mu js, the vertical component will cancel component, total net vertical component will be equal to 0. Hence mu j is given as the component of mu L around J, that is component of mu J about J star, and similarly we have component of mu S about J star. and this is given as EH upon 4 pi m naught L star, sorry, this is that is mu L, the component of mu L about J star, L star, and that is cos of L star and J star. You can take the value of mu L from the equation we already derived, that is EHL star divided by 4 pi m naught. This is the value of mu L, and we are taking the component of mu L about J star, so we are taking the horizontal component, we are taking the angle, and here we are taking the angle in between L star and J star. So we substitute this as an angle cos theta, and this is our value of mu L. Similarly, we can put our value of mu S from our previous derivation, that is EH upon 4 pi m naught, and here now it is 2 times of S star, and now we have to take the angle in between mu S and mu J, and let us consider this is our theta 2, and theta 2 is representing the angle in between S star and that is our J star. So we are taking the angle S star and J star. If we simplify it, we can take EH upon 4 pi m naught common, and in the expression we have cos of L star J star, which is representing the angle in between the L star and J star, 2 times of S star, and the angle in between S star and J star. Now we will find out the value of these angles, and you can easily find out the value of this angle, as you very well know that the addition of spin angular momentum and orbital angular momentum is equal to the total angular momentum. And if we have to find the angle between L star and J star, we will take L star in the side of J star, and we will have S star is equal to J star minus L star, and squaring both sides we will have S star square is equal to J star minus L star, that is whole square. And if you will open this bracket or this equation, you will have J star square plus L star square minus 2 times of J star L star, and cos of the angle in between J star and L star, which we can denoting in this way. And here we will easily find out the value of our cos L star J star, and cos L star J star in this case comes out to be, that is, if you will take this side, this term to this side, you will have J star square plus L star square minus S star square divided by 2 J star L star. Similarly, you can find out the value of the angle in between the spin angular momentum and total angular momentum, that is J star and S star. You will have J star square, and now you will replace L with S, then you will get J star square plus S star square minus L star square divided by 2 J star and S star. Now we will substitute these two values in our relation where we are finding out our total magnetic momentum or total magnetic field produced by our atom in this case. Now we will get mu J is equal to EH upon 4 pi m naught. We have L star, and instead of cos of L star J star, we are taking J star square plus L star square minus L star square divided by 2 J star L star, and with this we have the another term plus 2 S star cos of S star and J star, and Substituting this value in our relation, we have 2s star, and we will take j star square plus s star square minus l star square divided by 2j star and s star. And if you simplify this equation, you will easily find out that you will cancel out L star with L star and S star with S star, and you will have, taking LCM with this also, 2j star, we will get j star square plus L star square minus S star square from our first term, and from our second term you will have 2j star square plus 2s star square minus 2l star square. And on simplifying, you are finding out that you will get the total magnetic momentum mu j is equal to Eh upon 4 pi m naught, and this is 3j star square on solving, and here you will have plus s star square and minus l star square if you solve it here. And to make a square of everything, we are multiplying the term with j star and dividing the term with j star. And on again solving, we are simplifying our equation. We will have Eh upon 4 pi m naught times of j star, and here we are taking 2 j star square plus j star square plus s star square minus l star square divided by 2 j star square, and you will have a very significant term, that is 1 plus j star square plus s star square minus l star square divided by 2 j star square. Here we are again simplifying our equation, and we are taking it as Eh upon 4 pi m naught. This is a familiar term to you, and this is nothing other than the value of Bohr magneton. Well, what is Bohr magneton? It is the magnetic momentum produced by a hydrogen atom. If this value is Bohr magneton, then we have to multiply Bohr magneton with J star, and again we are putting this term, whole term uh, as a symbol G, where G is representing this term, and this term which is in bracket, and this term is like this. Very easy explanation. And G is nothing else than, it is known as Lande's G factor. Lande's G factor, it is not a constant term, it varies as the value of total angular momentum, spin quantum number and orbital quantum number changes, then the value of G changes. Here we in conclusion find out that our total magnetic momentum produced by an atom is represented by mu j, and it is equal to j star, that is a multiplication of our total angular momentum, where j star is representing j into j plus 1, where j is our total quantum number, and times g, where g is nothing other than our Lande's G factor, and this is in the unit of Bohr magneton. If you have to represent in the terms of SI unit, then you will have to give the expression EH upon 4 pi m naught times J star times G. You can use both of these expression to represent your atom as a atom dipole. It means this is the magnetic field produced by an atom itself. Until now, in our expression and in our uh, discussion, we doesn't have considered the applied or the external magnetic field. What will happen to this magnetic field when you apply an external magnetic field? Because we are studying the Zeeman effect, and in Zeeman effect we apply an external magnetic field. Now we are going to explain in what will happen to this total magnetic momentum when the magnetic field of strength H is applied. It means it is our applied magnetic intensity of strength H here we are representing. Let us consider our atom is producing so much of magnetic momentum, and we are applying this magnetic field in this direction, so that the mag- uh, magnetic field due to the atom makes an angle with the magnetic field which we are applying in the direction having an angle of theta in between the atomic magnetic field and the applied magnetic field. Due to this applied magnetic field, now the atomic magnetic field start to move around or start to process around this applied magnetic field, and due to which the energy of our atom will change, and the change in energy is due to the reason that our mu j is start moving around this applied magnetic field, and which is the component of mu j which is moving or which is forcing the mu j to move around the magnetic field H is our horizontal component, and this is our mu j cos theta. And we can give our change in the energy of our atom or our atomic magnetic field as that is mu j cos theta times of H, because if H is of high intensity, then the value of theta will also change, or you can say that the precision of our magnetic field, atomic magnetic field, depends upon the value of H. And in terms of Bohr magneton, we already know that mu j is nothing, it is our j star g, and cos theta, it is the angle between the mu j and that is H. We can say that it is the angle in between J star and H, because mu J and J star are in opposite direction, hence they are making the same angle with H. They are making vertical and opposite angles with H. If this is the direction of H, if this is theta, if this is J star, this is mu j, it means again mu j is making the same angle as J star is making with H, and with multiple times of our strength of magnetic field. And in terms of SI unit, if we have to give the change in energy, we will give our Bohr magneton in our relation which is given by that is EH upon 4 pi m naught. You have to give the mathematical relation of Bohr magneton, and now we have J star G and cos of J star H times of the applied magnetic field. You very well aware of this term, you are familiar about this term. This is nothing another than mg. This is our total magnetic quantum number, which is given by J star cos of J star H, and mg varies from plus J to minus J if J is an integer including 0, and if it is an half integral we will not consider the value 0. And mj have total values from plus j to minus j. We will have 2j plus 1 total values of mj. It means the change in energy is given as E h upon 4 pi m naught j star g h, and instead of j star we are putting these two terms j star cos of angle in between j star and h as mg. This is our expression for change in energy in case of anomalous Zeeman effect. If you remind of normal Zeeman effect, in normal Zeeman effect we have considered the result EHH upon 4 pi m naught and with the magnetic orbital magnetic quantum number. And this happens in the case of normal Zeeman effect, and in normal Zeeman effect we have considered s is equal to 0, and in anomalous Zeeman effect we have an extra term g, that is Landis factor with multiple of mj, because here we have considered the spin motion also. In this case we neglected the spin motion, and here we are considering the spin motion. If in anomalous Zeeman effect we neglect our spin motion, or we take s is equal to 0, we will find out that g, that is our Landis factor, which comes out to be 1 plus j star square plus s star square minus l star square divided by 2 j star square. If we put s is equal to 0, we will have j is equal, as we know that j is equal to l plus s, and if we are putting s is equal to 0, it means j is equal to l. And if we substitute these two conditions, that is s is equal to 0 and j is equal to l, what will happen to your Landis factor? J star square minus l star square, they will cancel out each other. This is equal to 0, and we will get, for these two conditions we will have g is equal to 1, and this is the condition of our normal Zeeman effect. Hence, with the help of anomalous Zeeman effect derivation, we can also find the formula for our normal Zeeman effect. In case of anomalous Zeeman effect, what we are going to discuss is that, for example, let us consider I have an energy level, and this energy level I am representing by 2p3 by 2, and in this case I very well know that this subscription term is representing the value of j, and this alphabet is giving me the value of L, and I very well know that this is nothing another than multiplicity. This is equal to 2s plus 1, and here this is equal to 2. It means in my case s is equal to 1 by 2. I know all the values of the terms to find out the value of g, and from the expression g is equal to 1 plus j star square, in terms of quantum mechanics j star is j into j plus 1 under root, and here I am putting the value of j star square. If I do the squaring of this, under root will cancel out the square root. Similarly, I will have s into s plus 1 and minus l into l plus 1 divided by 2j into j plus 1, and in our case we know the value of j is equal to 3 by 2, and if we put this value we will have 3 by 2 into 5 by 2, that is j plus 1, and in our case s, the value of s is half, and this term will become 3 by 2, and here in for p l is equal to 1, and here I will have this expression 2 into 3 by 2 into 5 by 2, and on solving all these factors you will get 4 by 3. And if this is your g is equal to 4 by 3, it means for the whole this energy term, this term is constant, because for this energy term there the value of j is not going to change, value of l is constant, value of s is also constant. If you are applying magnetic field h, that is constant, it means h is also not going to give the separation in between these, but we will find out for j we will have the different values of mj, and in our case this is half integral, then we will have the value of mj from plus j to minus j, taking all positive and negative half integrals, and we will have four values of mj. What is going to be in anomalous Zeeman effect? We have a energy term, and this energy term is representing by 2p3 by 2 when no magnetic field is applied. It means until we have no magnetic field applied on our atom. As magnetic field H is applied to our atom, our atomic magnetic field mu L starts to move around the applied magnetic field and moves in four directions, and these directions are given with the help of the value of mj. And in our case we have for mj is equal to 3 by 2, the change in energy is equal to, in terms of Bohr magneton, g times mj times h. And in our first case, when mj is equal to 3 by 2, the change in energy comes out to be 3 by 2 times of g into h. Similarly, for the second value of mj, the change in energy from the ground state, that is the undeviated state, when no magnetic field is applied, I will have the energy shift is equal to 1 by 2 times of Landis factor times of applied magnetic field. Similarly, for mj is equal to minus 1 by 2, I have an energy change of minus 1 by 2 times of g into h. And for the last case, minus 3 by 2, I got the change in energy is equal to minus 3 by 2 times of Landis factor and applied magnetic field. It means the separation between these energy levels depends upon the value of our total magnetic momentum, that is mj, and the applied magnetic field. Here in every case g is constant for a particular energy terms. When magnetic field is applied to this energy term deviates by four different type of energies depending upon the value of our total magnetic quantum number. Hence, one spectral line divided into four lines in presence of weak magnetic field, and this effect is known as anomalous Zeeman effect. magnetic field H is applied so that the interaction in between L and S is more strong as compared to the interaction of S with H or L with H. It means applied magnetic field should be weak, and the strength of applied magnetic field is compared with the interaction in between L and S. In anomalous Zeeman effect, L and S interaction is more strong as compared to the interaction in between H and S or in between H and L star.